Okay, so welcome back everyone to another APAC seminar. So today we've got Jackson Ryder from UNSW speaking, and he is talking about what is non-commutative algebraic geometry.
All right.
Take it
Thanks,
away.
thanks, Max, for the introduction, and thanks to the organizers for setting this up. So today I'm going to talk about what is non-commutative algebraic geometry. So just a bit of a quick overview of what we're going to do. We'll set up some commutative algebraic geometry background first to lead up to talk about a theorem by Serre, which is essentially our point where we jump off and go into non-commutative algebraic geometry. And then the last part, we'll talk about some connections with representation theory that arise. Okay, so let's get started. If I can get it to change slide, here we go. Talking about where algebraic geometry began. So originally we were interested in looking at solutions to sets of polynomials. So we're going to start by fixing algebraically closed field and take some set of polynomials in n variables, okay? With this set, we define the zero locus to just be all the points in kn, k to the n, which when evaluated at all these polynomials gives zero, okay? So just the common zeros of these polynomials. So sets of this form, so zero loci of polynomials, define a topology on affine n space, which is just k to the n, where these sets are the closed sets. All right. So this is what an affine variety is, essentially. It's just any set of this form, some zero locus of some polynomials, which we put the Zariski topology on, which is this topology we just defined, and we give it the subspace topology when it's sitting inside affine n space. Okay. So, did you have a question, Shirley? Okay.
No.
Okay. So now let's go the other way. Let's take a set of points in affine n space. We define the ideal of these points to be all of the polynomials, which when you evaluate them at every point in this set, give you zero. All right. And then if we have an affine variety, we define its coordinate ring to just be the polynomial ring quotient out by this ideal. So this correspondence here between zero loci and ideals gives us a bijection between finitely generated nilpotent free K-algebras and affine varieties. And more than just a bijection, it actually gives us like a contravariant equivalence of categories. So we can essentially view one as the opposite category of the other. Okay, so this is the foundations of algebraic geometry. So let's have a look at some examples. If we take this polynomial here, as you might expect, it gives us the circle embedded in affine 2 space. Okay. And then if we look at the zero locus of these two quadratics, it's just going to be their intersection. Okay, in this case, we get the points -1 and 1. And because this is the intersection of two quadratics, we don't need to embed it in 2 space. We can actually embed it in 1 space. Okay, just these 2 points here. All right. So now moving to the more modern approach to algebraic geometry, we might ask the question: what if we want to not just look at these special K algebras that we had before, but if we expand to all of commutative rings, what geometric object's going to sit on the other side of this correspondence? And that's going to be affine schemes. Okay, so what is an affine scheme? So let's take our commutative ring, and then the scheme spec R, so spec here is for spectrum, consists of 3 things. So we want the set of all prime ideals of this ring. Okay, we're going to put a topology on this set where we define it in terms of a base of open sets, which are just going to be all the primes in this spectrum, which do not contain the ideal generated by some element f in our ring. And as we let this range over all of the elements of our ring, this defines our base for our topology. Okay. And the last thing we need is a sheaf of rings. So don't worry too much about this. Essentially, we just assign to each of these basic open sets a ring, which is going to be the localization of our ring R at that element. And when we have an inclusion of sets, open sets, we get a surjection of rings. Okay, but that's not too important for the moment. Okay, so these affine schemes actually recover all the information that are contained by varieties. So if we just looked at maximal ideals, this would give us all the information that we had from a variety, but now we get actually more. It's a richer kind of theory because these prime ideals, which aren't maximal, give us information about like open subvarieties or subschemes. Right? So we get a bit more than what we had with just varieties. And so we can look at some examples. If we take the integers, we get all of the prime numbers give us a prime ideal. So we get a point for each of these. And then off on the side, we kind of have 0 because the 0 is a little different. In some sense, it's not just a point, it's everywhere along this line, because when we take the closure of this open set, it gives us the whole space. Okay, so this is something new that arises when we go from varieties to schemes. And if we look at this ring, so we take our polynomial ring and we mod out by y squared and xy. So we do just get, well, the polynomial ring in one variable, which is our affine line. But around 0, we have this kind of fuzziness. And what this is representing is that we remember first order differential data around the point 0. Okay, so this is something that comes up when you have nilpotents now in your rings. So another thing that's different with these affine schemes. Okay, so that's all well and good, but there are some issues that come when we're working with like affine schemes. So in particular, affine space is not compact, which is it's not always a problem, but it's nicer if we're working with a compact space. So what do? Well, we're going to compactify it. Okay. For affine n space, just like you would expect, compactifying gives us the projective n space, which is just affine n plus 1 space minus the origin, and we mod out by the action of the multiplicative group. Okay, so our first pass at a definition of a projective scheme is just going to be any closed subscheme of projective n space. So at the moment, this doesn't really mean much, but it'll give us some ideas of what we need from a projective scheme. And then on the next slide, we'll go on to give a more useful definition. Okay, so given that we have this invariance under the multiplicative group, this tells us that all of our functions have to be homogeneous in the sense that if we scale a point by some constant lambda, it's the same as acting on just the point and pulling all of the lambdas out the front. So we get lambda to the degree of our function, okay? And what this tells us is that we have a very natural grading on the coordinate ring of a projective scheme, just given by the degree of our functions, okay? So now this leads us to work with these Z-graded rings. And we want to know, can we do something like the spec functor that we had before, assigning a projective scheme to a graded ring? So this is what we call the proj construction. So we take our commutative Z-graded ring and we construct a projective scheme, proj R. It consists of the following. So this is going to be very similar to the construction of the spectrum of a ring. So now we start with our set of prime ideals, but we want to insist that they have to be homogeneous because, well, for the reasons we mentioned before. And we also have this technical condition that the ideal generated by just all of the elements of positive degree is not contained in any of these primes. Okay. We're going to define a topology just like we did before. Okay. Define our topology. It's going to be the exact same as the topology we put on the spectrum, but now we're ranging over the homogeneous elements of our ring. And then lastly, we have a sheaf of rings again. Same as before, except now when we localize our ring, we're taking the degree 0 component only. All right, cool.
What do you mean by a homogeneous prime ideal?
Yeah. So it's just like all the monomials have the same degree. So it's just I'll just go back to the previous slide. It just means it satisfies this condition.
All the elements satisfy that?
Yeah, all of the functions.
Uh-huh.
So yeah, if you scale by a point, you just pull that out to the degree of, which is the same as like all the like different monomial components of your function having the same degree.
Mm-hmm. Yeah. Right. And what's this Z graded condition and why is it important? Yeah.
So, well, if we insist on this, it just gives us a natural like grading by degree.
I see.
Because all of the components have to be the same degree. So
right.
It gives us the structure of this like a graded ring.
Yeah.
Okay. Sweet. Okay. Okay. So yeah, now we have this way of constructing our projective schemes from these graded rings. But unlike in the case of like the spec functor, this proj isn't functorial. So two different rings can be assigned the same projective scheme. So this isn't awesome, but we do have a way of getting around this in some sense. So luckily, algebraic geometry had Grothendieck hanging around, and one of his 7,000 brilliant insights was that we shouldn't just study the ideals of a graded ring. We should look at all of the modules. Okay, so if we have a projective scheme, a sheaf of modules over that scheme is just an assignment of, well, this OU, this is our sheaf of rings we had. So every open set is assigned a ring. And then when we're constructing a sheaf of modules, we just assign a module over each of those rings corresponding to the open sets. And we want to have it so that anytime we have an inclusion of open sets, we get a surjection of these modules. Okay. So you can think of this, the sheaf of rings is essentially just you're sticking a ring onto each open set in a way that's compatible with your inclusions. And then this sheaf of modules is just doing a module over all of those rings. You want it to be compatible with these inclusions as well. Okay. So this proj construction also extends to graded modules. So it's not too bad to see where this comes from. So if we have a graded ring and a graded module over this, we get a sheaf of modules over the proj of that ring. Okay. One thing that we need to keep in mind, and will actually be quite important later, is that the assignment of a module to this sheaf of modules over the proj of the ring isn't unique. So two modules are going to give you the same sheaf of modules if they only differ in a finite number of graded components. Okay, so if eventually you can go far enough along in the graded components and they're always the same, then they're going to give you the same sheaf of modules. Okay, and the last thing that I'll quickly mention is that we can also go the other direction. If we have a sheaf of modules, we can look at the global sections, and that's going to be a module over the coordinate ring of our projective scheme. Okay, sweet. So just like in differential geometry, right? We want to kind of look at vector bundles, so things that are locally free. So in our case, this would be sheaves of modules that are locally free, which we also call vector bundles. But unfortunately for us, they don't form an abelian category because our co-kernels, we don't necessarily have all the kernels and co-kernels that we need, which means we can't do homological algebra essentially on these vector bundles. This is sad. So what do? Well, we kind of just throw in all of the co-kernels that we need and work with this larger class of objects. So we say a sheaf of modules on a scheme is quasi-coherent essentially if locally we have a free presentation, okay? So at any open set, we can take a free presentation of this module, sheaf of modules restricted to that open set. All right. So here, these index sets I and j can be infinite, but if we insist that they have to be finite, and also that at every point in our scheme, we have some neighborhood on which we're locally finitely generated, we call this sheaf of modules coherent, okay? And these coherent sheaves of modules are exactly what you get if you just take the vector bundles and you throw in all of the co-kernels of morphisms between vector bundles, okay? So it's the smallest abelian category that contains all of your vector bundles, all right? So yeah, like I just mentioned, both of these categories are always going to be abelian, which is great for us because now we can do all the homological algebra that we like, okay? And also, under some mild hypotheses, our projective scheme is determined by this category of quasi-coherent sheaves, okay? So I think we just need that our scheme is quasi-separated and quasi-compact for people who are familiar with what those mean. But then we can determine our projective scheme from this category of quasi-coherent sheaves. All right. So now, so now we come to this theorem of Serre, which is very nondescript because that could mean any number of results from Serre. But the one that we're concerned with is to do with this category of quasi-coherent sheaves and giving it a description in purely algebraic terms. So we're going to add some hypotheses onto our graded ring now. We're going to let it be generated in degree 1, meaning that we have a finite set of generators, all of which have degree 1. Okay. And we're also going to insist that the degree 0 component is just a field. And now we'll let X, I guess, be our proj of this graded ring. So the two maps that we defined before, I guess taking the proj of a graded module, which gives you a coherent sheaf, a quasi-coherent sheaf, sorry. And then this global sections functor, which takes a quasi-coherent sheaf and gives you a graded module. So these are not just maps, these are actually functorial. And moreover, we have this theorem from Serre. There's quite a lot to unpack here, so we'll go through this slowly. We're going to start by defining the torsion subcategory of our graded modules. So it's just going to be the full subcategory of finite length objects. So graded modules that have a composition series, a finite composition series. Okay. These two maps, or functors, sorry, this like proj of a module and this global sections functor define an equivalence of categories between the quasi-coherent sheaves on X and the quotient of the graded A modules by the torsion subcategory. So we'll come back to this idea of a quotient of a category by a subcategory in a second. And hopefully I'll convince you that I'm not just making something up here. And furthermore, if we restrict to the coherent sheaves on X, then this equivalence restricts to the finitely presented objects in the graded modules and in the torsion modules. So when we look at just the finitely presented objects, which are also finite length, these are just graded modules, which only have a finite number of non-zero graded components. Okay, so they're very finite in a sense. So before we do anything else with this theorem, I'll just quickly talk about this idea of a quotient of a category by a subcategory. So we're going to take a subcategory of some abelian category A. We say it's a Serre subcategory if for every short exact sequence in A, we have that our middle term is in the subcategory if and only if the two outside terms are. So it's a subcategory that's closed under subobjects, quotient objects, and extensions. Okay. So now, so yeah, our torsion subcategory that we defined before is one of these Serre subcategories, because if we have something with a finite composition series, any subobject, any quotient object, and any extension of these is also going to have a finite composition series. Okay. So now if we take a Serre subcategory, we can define the quotient of our abelian category A by this Serre subcategory. It's going to consist of two things. So we want an abelian category, which we call A on T, and we want an exact functor from A to this quotient, which sends all of the objects in T, our subcategory, to 0. Okay, well, we set them isomorphic to 0. And we want this to be universal with respect to these properties, in a sense that if we have any other abelian category and a functor from A to that category, which sends all of our objects in T to 0, it should factor through this category, A on T. All right. So this is how we define our quotient by a Serre subcategory. Right. And so I have defined this in terms of a universal property. I'll flash up the construction here. For your own sake, don't try and read this. It's not going to be enlightening in any way. I'm just showing you that it does exist. We can construct it. Okay. So let's move on now. And let's talk about some non-commutative schemes. So we're going to shift now, and we're going to take a non-commutative graded ring. And it's natural to ask, can we just do proj of this non-commutative ring? And I guess you can, but when our ring's non-commutative, we don't have many two-sided ideals floating around, if we have any at all. So if we have a non-zero non-commutative ring, the proj of this ring could be empty. Okay, so that's the main issue that comes if we try and just do the same commutative algebraic geometry techniques with a non-commutative ring. But our idea now is, rather than working with some non-commutative space, we should work with just coherent sheaves. And the reason why is because this construction of these two quotient categories that arose in Serre's theorem before is not affected by commutativity in any way. So our non-commutative rings might not have many ideals, but we always have plenty of modules floating around. So this is why we work with these quotient categories. We view them as being the coherent sheaves on some non-commutative space, which doesn't really exist, but the coherent sheaves on it do, okay? And like we mentioned before, with that reconstruction theorem, in most cases, the quasi-coherent sheaves actually determine our scheme. So it's not entirely unfounded to work with that category of quasi-coherent sheaves. So yeah, this is where we're going to jump off and get into some non-commutative algebraic geometry. So we'll see why this is actually useful and we're not just playing around with something for the sake of it. So before we do, actually, we're going to quickly talk about a special type of rings that arise a lot in this non-commutative setting. So if we just have our graded ring, we get a free endofunctor on the category of graded A modules, where we change the grading of a module. So we send the degree n component to the degree n+1 component. Okay, this is very useful to have floating around. So the question we pose is, what happens if we're working in some funky abelian category and we have a sequence of objects that look like all the different shifts of our graded ring? So here this shift I just means applying the shift 1 functor I times. So what if we have something that looks like this, but we don't have any endofunctor that we can find lying around? So if we go back to looking at our graded ring, we can recover it from this sequence by just looking at the sets of morphisms between the objects in this sequence. So we had this chain of isomorphisms here, which shows how we can recover our ring from just this sequence of objects. So this is the motivation behind defining these indexed algebras. So we say that a Z-indexed algebra is a pre-additive category. So that just means that our sets of morphisms are abelian groups. And we insist that the objects are indexed by the integers, okay? So to one of these things, we associate a set of morphisms, or the ring of morphisms, like we did before, where we look at all of the HOMs between the objects in the category. And this becomes a ring when we let our multiplication just be composition of these morphisms. Okay, so so these are unfortunately named. They're called indexed algebras, but in most cases, it's just going to be a ring. I'm not sure why this name has stuck around, but it's just one of those things that we deal with now. Okay, so let's see some examples of non-commutative projective schemes and see why these indexed algebras are useful to us. So, okay, we're going to start by talking about graded rings. So any graded ring actually gives us an indexed algebra, where we set the ij component to just be the j minus I component of our ring. Okay, so in a sense, we see that these indexed algebras are somewhat an enlargement of the class of graded rings. And what's more interesting, maybe, is that the modules over this indexed algebra are essentially the same as the modules over our graded ring. We have this equivalence of categories, which is very useful for us, which we'll see now with this example of skew polynomial algebras. So we'll let AQ just be the free algebra on two generators, quotient out by this relation here. So when Q is equal to 1, this is just going to give us our regular commutative polynomial algebra. But if Q is not equal to 1, it's going to give us something like very non-commutative. So those graded rings, AQ and just A1, are obviously very different. Like one's commutative and one's not. But actually, the indexed algebras that come from them are isomorphic. So don't worry too much about these maps. These are just the maps that define this isomorphism of indexed algebras. But it essentially comes from having generators in every degree, and we can kind of define this isomorphism going across the different degrees. So this is very useful because remember that the graded ring and the indexed ring have the same modules. So if we look at the quotient category, so essentially the non-commutative coherent sheaves on proj of AQ, well, because these graded modules are equivalent, these quotients are also going to be equivalent. And A1, just the commutative polynomial ring, gives you the coherent sheaves on the projective line. So when we're looking at these skew polynomial algebras, we can think of them as being sort of non-commutative projective lines. Okay. So these are, I guess, not very interesting examples of non-commutative P1s because these algebras are actually like very close to being commutative, even though it might not seem it. But it's still a fun little introduction, I think. So for the last part of this talk, we're going to do some representation theory and see how this idea of non-commutative schemes can give us like new insights to different areas. So we're going to start by looking at the representation theory of finite-dimensional C algebras. So for anyone who's familiar with this kind of theory, you'll know that it just reduces to looking at representations of quivers. Okay. So this is going to be our favorite quiver for the rest of the talk, this Kronecker quiver, 2 vertices and 2 edges between. So how do we construct a representation of this? Well, we're going to assign to each vertex a copy of our field. And then to each edge, we're going to assign a one-dimensional vector space over C. Okay. So this thing that we're constructing now, we call the path algebra. Hopefully we'll see why in a second. Just to condense this, instead of having 2 edges with a one-dimensional vector space, we kind of crush them together and just have one edge, and we take the direct sum of both of these vector spaces. Okay. So this is essentially just recording that we have 2 different paths or 2 different edges between these vertices. So now we let R just be the product of C and C. So if we had a bigger quiver, we'd take the product of all of these fields that are assigned to the vertices. And M, we take the sum of all of the vector spaces that are assigned to the edges. Okay. And then our path algebra is just going to be the tensor algebra on this vector space, which records all our edges. Okay. So if we had a bigger quiver again, we'd have a component here where we take M tensor M and so on and so on. But in our case, M tensor M is just 0. Okay, so this is our path algebra. So then a representation of a quiver is just a module over this path algebra. All right. Okay, so I'll hold on a second. So this idea of studying these representations, it's been around for a long time. And there's a very, very nice connection between algebraic geometry and these representations of quivers and these path algebras. So if we take this, this vector space M, just the sum of all of the vector spaces on the edges in our quiver, and we look at the symmetric algebra on this vector space M, then when we take the proj of this symmetric algebra, it's actually going to give us the projective line. And we have a derived equivalence between the coherent sheaves on P1 and the finitely presented modules over this path algebra. Okay, so this functor from this coherent sheaf this Hom functor actually determines this equivalence. So this is called a tilting bundle here. And this idea of tilting allows us to take algebro-geometric ideas and translate them over to this representation theory. And that's a very deep, rich kind of theory that's been around for quite a while now. And it doesn't just work for P1, I guess. Any projective variety is going to have a tilting bundle on it, which will tilt to the path algebra of some finite acyclic quiver. Okay, so this is all well and good, but we're not just interested in finite dimensional C algebras. We want to know about R algebras and Q algebras and algebras over non-commutative, non-algebraically closed fields. So let's have a bit of a look and see what happens when our field isn't algebraically closed. So this is our C algebra that we had before. And we'll see how what the actual connection is between C algebras and path algebras of quivers. So if we take its radical, we just get the strictly upper triangular entry. So then we can look at A mod its radical, which is going to be C times C, the diagonal here. And then we can look at the radical mod its square, which is going to be C squared. And if we had a bigger algebra, we would continue this looking at the square of the radical mod the cube and so on, which when we sum these all up together, we just recover our algebra A. But hopefully this will be looking familiar to you all, because when we take this direct sum, we get C times C plus C squared, which is just the path algebra of that quiver that we had before. Okay. So this is kind of where we see this connection between finite dimensional C algebras and path algebras of quivers. We can construct a quiver using this process such that the path algebra of that quiver is just the algebra that we started with. But what if we're not algebraically closed now? So let's do the same thing, but now we've got this R algebra, where our diagonal is the complex numbers and the quaternions, and our upper entry here is also the quaternions. So if we do the same thing that we had before, we define this radical, which is just, again, going to be the strictly upper triangular part. And let's look at B mod its radical. So again, we get the diagonal, which is just going to be C times H. And we take the radical mod its square. So now we get the quaternions, but as a C, like a complex numbers and quaternions bimodule. So we have a left complex action and we have a right quaternion action. Okay. So well before to our vertices, we'd assign our field, and to the edges, we'd assign a vector space over that field. When we're not algebraically closed, we actually don't just have the field. We want to look at all the division rings over the field. So our vertices, we can assign division rings. And then to the edges, we assign bimodules over those division rings. So that's our more general kind of notion of a path algebra, I guess. So let's look at another example. So we're back to this Kronecker quiver. So now we're going to put two fields here. So one field for each vertex. And just like we did before, so we put a bimodule over these fields instead of a vector space now. And because, remember, we have two edges here, we're going to insist that this bimodule has dimension 2 on both sides. Okay? We're going to take the product of these fields, just like we did before when they were just C. And this tensor ring, so this is our generalization of a path algebra. It's called a tensor ring. And it's just going to be the same. You look at the tensor algebra of the bimodule over this ring. So it's just, in our case, it's just K0 times K1 direct sum F. Okay. So this more general assignment of like division rings to the vertices and bimodules to the edges, we call a bimodule species. Okay. Cool. So now we want to know if we can do some sort of tilting like we did before to study these tensor rings and these bimodule species using some algebro-geometric objects. And in fact, we can. So before, remember, we took the vector space determining or counting the edges basically, and we looked at the symmetric algebra over it. So now we're going to do a similar thing, but we want a non-commutative symmetric algebra, as counterintuitive as that sounds. So we're going to start by defining the index tensor ring. Here's another unfortunate thing where we've decided to call both of these things the tensor ring, but I'll specify that this is the indexed one. So we define this index tensor ring on the bimodule F. It's going to be the Z-indexed algebra now, where the ij component of this algebra is going to be 0 if j is less than I. If I is equal to j, we're essentially just going to alternate between the fields. So we take the residue of I mod 2, and it'll be k, that residue. So we're going to go k0, k1, k0, k1 over and over again. And if I is less than j, we're going to take the product of joules of this field. So we'll start with this I joule, which just means you take the joule of this bimodule like I times, and then we'll tensor it with the I plus 1th joule over the appropriate field. And we continue on until we get to tensoring with the jth joule. Okay. So the reason that we do this now is because we can't just tensor F with F. So when we're constructing the symmetric algebra on a vector space, you just take V tensor V mod the commutativity relations. But now because we have a bimodule, we can't just do that. So we have to take the joule to make sure our actions are compatible when we're doing this. Okay. So now if we take this index tensor ring and we quotient out by some, well, commutativity relations in each degree. So that's what these are down here. It's not super important at this point what these are, but they're just our analog of the commutativity relations we have for the symmetric algebra. So if we quotient out this index tensor ring by this, we get the non-commutative symmetric algebra of this bimodule F. Okay. So it does at first seem very counterintuitive to have a non-commutative symmetric algebra when the idea of the symmetric algebra is to be commutative. But this actually inherits a lot of the same useful properties that the symmetric algebra has, but for a bimodule now instead of a vector space. And also, we have a version of our tilting result that we had before for these non-commutative symmetric algebras. So if we take a bimodule, like we had before, with this tensor ring, so the tensor ring is associated to the bimodule species, then we have this derived equivalence again, but now we have this quotient category of the non-commutative symmetric algebra being derived equivalent to the finitely generated modules or finitely presented modules over this tensor ring. So here, this is replacing the coherent sheaves on some projective scheme. So this is our coherent sheaves on this non-commutative scheme. And we have this same relation. And this result actually holds more generally for any division rings K0 and K1 and any bimodule. So we don't have to insist that it's dimension 2 on both sides, as long as we have that the left joule and the right joule are isomorphic. Okay, sweet. And so we have this more general version of this equivalence, okay? And this idea of studying bimodule species has been around for a long time, since the, I think the late 60s, early 70s is when it first came up. But it kind of all stopped in the 80s because, well, I guess the algebraists at the time studying these things kind of decided that they'd done all they could. It was too hard. There was nothing more they could do on the topic of like classifying the indecomposable modules over a bimodule species. But with this new kind of perspective we actually get some more information that wasn't available or wasn't known to the algebraists at the time. So if we take a bimodule, so now we're going to insist again that they're K0 and K1 are fields and dimension 2 on both sides. We get a family of elements in this non-commutative symmetric algebra, a family of elements which are in degree 2, such that when we left multiply by gi, it's the same as like right multiplying by the correct corresponding element. So this is the like a generalization of the idea of having a normal element in your graded ring. And we like normal elements because they play very nicely with localization. Localization of non-commutative rings tends to be a bit of a pain. You end up with, sometimes you can localize, but you only get a right ring of fractions and not a left ring of fractions, and so on and so forth. But normal elements we like because when you localize, you get a two-sided ring of fractions. So this actually is a generalization. So given that we're working with these indexed algebras, we can't just have one element, but we have a family of normal elements here. And this is useful because this, well, this is known in the commutative case. And it's very useful because if we quotient by this, this ideal generated by these normal elements, we get something which looks like a homogeneous coordinate ring on an elliptic curve. And all of this has been like very well studied in the commutative case. So this actually gave us some more information about this non-commutative symmetric algebra. And it was used to show, for example, that it's Noetherian, which is in general very hard to show. And it wasn't known to the algebraists of the time. But yeah, we get this Noetherian, and we get some other useful information from this as well, concerning specific types of indecomposable modules that we're interested in. But yeah, okay. Thanks everyone for listening to this. Hopefully you got something out of it, a bit of an idea of what we do with non-commutative algebraic geometry. Thanks.
Thanks for your talk, Jackson. Does anyone have any questions? Yeah, well, I mean, I don't really have a specific question, but I'm curious. So you study non-commutative algebraic geometry.
Yeah.
And I'm wondering how much studying the geometric perspective here helps one understand, say, the structure of non-commutative rings, or is non-commutative algebraic geometry like really motivated by just understanding the geometric picture?
Yeah, so I'm just trying to think. I'm not sure that we do gain much insight from like about non-commutative rings. It's more that like we use a lot of the knowledge that we have about non-commutative rings.
Mm-hmm.
So yeah, that's kind of yeah. I guess in some cases, because a lot of the times we're guided by the commutative case. So we know what sort of conditions should hold for certain types of non-commutative schemes.
Mhm.
Like this non-commutative ring, this non-commutative symmetric algebra. Like in the commutative case, we know it's Noetherian. So we should hope that it is also in this case. And we actually, well, yeah, my supervisor, Daniel Chan, proved this result, like found these elements that they essentially correspond to the equation of an elliptic curve. So that's how like they knew to look for it, because if you have an elliptic curve, it has some equation that defines it, and you can quotient out by that and get the coordinate ring. So we knew that my supervisor knew that something like that should be there and was able to actually find it, take this quotient, and this quotient is very obviously seen to be Noetherian. And you're actually able to pull that back to the original ring. So.
And do non-commutative rings have a very large theory? Like, are they reasonably well understood, or is
there's a large theory. I'm not sure how much we understand though.
Yeah.
In some cases, but yeah, it's much more complicated, and like you get a lot of different types of things happening.
Okay.
Yeah.
Was there any other questions?
I had one from right back near the start of the talk. So I think
how far
when
back are we
you
going?
started talking about sheaves, all your sort of restriction maps were surjective.
Yeah.
Yeah. Is that necessary? That seemed, because that's, yeah. Is that necessary for all this to work?
Yes. So it's kind of, I guess I didn't really talk about it a lot. What did I say? But so the way that these sheaves arise is kind of as contravariant functors to other categories. So if we look at this as just like a topological space, a sheaf of rings is just the contravariant functor from like the category of open sets here, where the morphisms are inclusions, to the category of rings. So the reason that we want them to be surjections is that all of our morphisms in this category are inclusions, right? Because they're inclusions of open sets. So they're always going to be injective. So when we apply this contravariant functor, it's going to turn those into surjections.
Okay. All right, sure. Thank you.
That's all good.
Was there any other questions? Okay, well, if there's no questions, let's thank Jackson again and we can finish up here.
Awesome. Thanks for having me.
Thanks for speaking.